In this lecture, let us discuss a demodulation of DSB as a signal. If you recollect, in the last lecture, we have studied the concept of amplitude modulation. We were discussing one kind of amplitude modulation which is called double sideband. With suppressed carrier. Amplitude modulation. Okay, so this in short we called DSB AC AM modulation. Okay, so we have looked at the waveform, we have looked at the spectrum, and we were looking at the demodulation for such a system. So how do we demodulate from the modulated signal? Okay, so that means how do we get the message signal back from the modulated signal? And okay, so we can say that the demodulation process could be very similar to the modulation process. So what is your modulated signal? X of t is equal to m of t multiplied by the carrier. Carrier is a times cos of omega ct. Okay, so this is your x of t. So the received signal x of t is equal to a times m of t times cos of omega ct. Once again we have to go through the frequency translation process. In the modulation we have done the frequency translation. So the same kind of opposite kind of frequency translation process we need to do here, so that we get the component around 0 Hz frequency. So that is the baseband component. Of course, in the process we will get a component around 2 Fc as well. Therefore, the demodulator will have the same multiplier that we have at the transmitter. So you have the received signal x of t, give it to a block consisting of multiplier, and the input is modulated signal, and the other input is 2 times of cos omega ct. I have taken 2, okay, just for sake of removing some constant. It's not necessary to take 2, you can take anything. And this, let me call the output of this waveform is z of t, and this is given to a low pass filter, and this output is, finally you are getting the output, that output is your message signal. Okay, so the receiver will multiply the received signal x of t with the carrier 2 times of cos omega ct, okay, and followed by an low pass filter. Okay, followed by a low pass filter. Okay, now hopefully this one will be the replica of, let me put m cap of t, replica of the message signal m of t, we will assume. So mathematically speaking, your z of t is equal to received signal multiplied by 2 times cos of omega ct. Okay, so therefore z of t is equal to multiply x of t. X of t we know, a times m of t cos omega ct. Therefore 2 times a times cos omega ct times m of t cos omega ct, then this is 2 times a times m of t cos square omega ct. Now let us assume this is equal to some constant, let us say k. Okay, no, let it be as it is, don't disturb that. Okay. Okay, fine. Now what you do, this is cos squared term. So this cos squared term you replace in terms of trigonometric. So I can write 2 times a times m of t times cos square theta. I can write 1 plus cos of 2 omega ct divided by 2. This 2 and that 2 will get cancelled. So it is equal to a times m of t multiplied by 1 plus cos of 2 omega ct. So this is equal to a times m of t plus a times m of t cos of 2 omega ct. Okay. Now this is constant, a is some constant, so it's some amplification factor. You can disregard that. Okay. If I take Fourier transform of this signal z of t, this is my z of t, capital Z of f is equal to a times capital M of f plus a times within a bracket m of f minus 2f, because 2 omega ct now. Okay. So 2fc plus m of f plus 2fc. Okay. Now from this, which is a desired spectrum, this one is a desired spectrum we want our message signal, we don't want anything else. Okay. Desired spectrum. Okay, if you plot this desired spectrum in the frequency domain, you have let's say this is your m of f, and now it is 2 times of your frequency. This is minus 2fc plus b, and this one is minus 2fc minus b, and if you come this side, then it may have like this, that is 2 plus 2fc, and this one is 2fc plus b, and this point is 2fc minus b. Okay. Now if you pass it through a low pass filter with the cutoff frequency fc, fc is equal to b, this is plus b and this is minus b. This portion alone will be passed through the low pass filter. Okay. And this one is, what is this? This is, I am sorry, this is z of f, and this one is m of f, and this guy is m of f minus 2fc, and this one is capital M of f plus 2fc. So in addition to m of f, you have 2 components. Okay. In addition to m of f, you have 2 components. What are those 2 components? This one, m of f minus 2fc and m of f plus 2fc. Okay. And what is this one? This one is the translated version of your m of f around 2fc, and this one is translated version of your m of f around the frequency minus 2fc. Okay. So I have 2 additional component with the desired message signal or desired frequency component. Okay. So bandwidth of m of f is the largest frequency in m of t. Okay. Now you choose let's say this is my low pass filter. Then this is my cutoff frequency. Don't confuse, maybe I will write down something else because here also there is suffix c and here also suffix c. So let me write some other notation. Cutoff frequency, let me put f alpha. Okay. F alpha is the cutoff frequency of the low pass filter, and let us choose this f alpha greater than b. Okay. But much less than, sorry, if f alpha much less than what, your fc. But in fact, this condition is not needed. If this condition is satisfied, that is enough. Therefore, this is your low pass filter like this. Therefore, comfortably it passes the m of t to the output. Okay. So if this condition is satisfied, cutoff frequency is greater than b, then obviously it will be obviously the cutoff frequency is less than 2 times fc. See, this is 2 times fc and much less than your f alpha. Okay. Therefore, these two components, this component and this component will not overlap, because see, this m of f, then m of f plus 2 fc, then m of f minus 2 fc, all are non-overlapping spectra. Okay. So m of f minus 2 fc or plus 2 fc has much higher frequency band than that of your m of f. Okay. Therefore, it would be very easy to separate m of f and m of f plus 2 fc. Similarly, it is very easy to separate m of f and m of f minus 2 fc. So the low pass filter should have a bandwidth of b. So low pass filter should be with a desired bandwidth of b. That is what you want. So we want only the desired signal. What is the desired signal? M of t. M of t. Desired signal in the frequency domain, capital M of f. Okay. And then naturally the components which has centered around 2 fc, this guy and this guy, this is plus 2 fc and this one is minus 2 fc, both are eliminated from by the low pass filter. Okay. So in the frequency domain, what we have is, let me draw the figure once more. So this is your m of f, and let's say your low pass filter characteristics like this. Okay, this one is m of f and this one is a low pass filter, and somewhere sitting your 2 fc, and this side somewhere sitting around minus 2 fc. So this portion will be eliminated and this also will be eliminated. Only this is passed through the low pass filter. Okay. So minus b2 plus b is the desired component. So if you have a low pass filter with the response like this dotted line, low pass filter, then the signal, then this guy and this guy will get eliminated, and then what you get in the output is the product of low pass filter and this guy m of f. Okay. So this response m of f and this response low pass filter. Therefore, we will just get m of f back. Okay. So that's the demodulation. It looks simple enough. Okay. So there is a small complication, even though it looks very simple enough, there is a small complication which you should be aware of. Let us see what that complication is. Okay. The demodulator, if you look at what is a demodulator, incoming signal x of t is multiplied by the locally generated carrier 2 times of cos omega ct and followed by a low pass filter. So this is my demodulator. Okay. Now in this demodulator, it requires a carrier at the receiver. This is my carrier again, right, because cos omega ct, the same carrier we used in the generator also. So therefore the receiver needs a carrier with the same frequency and the same phase. Therefore at the receiver I must have a replica of the carrier that I use at the transmitter. Okay. And it looks like that does not appear to be a very big deal, but you must remember that there is a requirement here. What is that requirement? This local carrier 2 times of cosine omega ct must be precisely the same frequency as the one that we have used at the transmitter. If that is not exactly equal, then there will be some problem. That problem, we will see what that problem is. So you should have precisely the same phase as the phase of the incoming signal, incoming carrier signal. So phase must be precisely the same of the incoming carrier signal, and frequency must be precisely the same as the carrier frequency, and phase also. Precisely the same phase as the incoming carrier signal. Otherwise, you cannot demodulate. Let us see why we cannot demodulate. Okay, so the input was cos omega ct. The modulation has been done by multiplying m of t with the a cos omega ct at the transmitted side, and we are assuming that the perfect knowledge of frequency and phase at the receiver. We assume that, okay, so the receiver produces the carrier which has the knowledge of the incoming carrier signal phase, and also the frequency will be same, so that you can multiply it by the local carrier, that is a replica of the local carrier, and you get your demodulated output. So implicitly this is a demodulation process. Okay, so there is something called a concept of synchronicity. Okay, so if these two are matched, then that is called synchronicity between the transmitted carrier and at the local carrier at the receiver. So this is also called synchronous demodulation. This whole thing is called why is it synchronous modulation? Because the carrier has the knowledge of incoming carrier's phase, and also the frequency which you are generating locally, that will be equal to the carrier which we used to modulate the signal at the transmitter. Okay. Therefore, the local carrier at the receiver should be in the perfect phase and frequency with the carrier of the received signal. If it is not so, you will not get a perfect demodulation. Okay. If frequency is not the same as not the same as the carrier frequency, and if there is some phase mismatch, then you will not get a perfect demodulation. Okay. So let us see why. So let's look at the effect of loss of synchronization. Okay, if synchronization is not there, then what will happen? In your synchronization, if your synchronization is not perfect, what will happen? Let us say this is your z of t, right? Now let me take the same circuit. Now the carrier is slightly different from let us say 2 times cos of omega ct, but slightly mismatch from the carrier frequency. Let us say that mismatch is delta omega t. Okay, and phase mismatch, that phase mismatch let me call theta. So like that your carrier is produced at the receiver, and the incoming signal is, let me call x of t, and this one is, now let me call y of t. Okay, instead of z of t I am calling like this. Now low pass filter. Now the same operation, what is your y of t? Same mathematics you go through. Y of t is equal to x of t times your locally generated signal, 2 times cosine of omega ct plus delta omega t plus theta. Now what is x of t? X of t is equal to a times m of t times cos of omega ct times 2 times cos of omega ct plus delta omega t plus some phase angle theta. Now 2 times a times m of t, then now this is not cos squared, okay, cos a cos b. So cos A cos B, we know the formula, you just okay, substitute that. So this is multiplied by cos of A plus B, therefore cos A cos B equal to cos A plus B plus cos A minus B. So 2 times omega ct plus delta omega t plus theta, this is one component, plus cos of omega ct minus omega ct becomes 0, therefore you will get delta omega t. This delta omega is very very low frequency, okay, small variation. Let's say your let's say if omega c is equal to let us assume fc, carrier frequency equal to 1000 kilohertz, then your delta omega may be some 10 hertz, like this, very small variation from the carrier frequency, 10 hertz, maybe 1 hertz to 10 hertz, that is the delta omega t. I mean it's not delta omega, it is delta f in terms of normal frequency, not angular frequency. Okay, so delta omega t plus theta. Now multiply this term by term, 2 times A times m of t cos of 2 omega ct plus delta omega t plus theta plus 2 times A times m of t cos of delta omega t plus theta. Now what are you doing? You are passing it through this y of t is passed to the low pass filter. Okay, so maybe I will call this guy also z of t, no issues, and this one let me call y of t. So let me say this is my z of t. Now after passing through the low pass filter, z of t is passed through a low pass filter. So what will happen if you put a low pass filter? Say this is a high frequency component, 2 times of omega c, therefore the entire term will be rejected by the low pass filter. So the output y of t contains only 2 times A times m of t times cos of delta omega t plus theta, delta omega t plus theta. This is my y of t. Now let us assume that frequency is at least perfectly synchronized. Okay, just let us consider two cases. Now in case 1, assume the incoming carrier frequency and locally generated carrier frequency both are perfectly synchronized. So if it is both are perfectly synchronized, then that means what? Let us assume delta omega is equal to 0. So your received signal y of t is equal to, let me put this 2 times of A as some constant k, then m of t and cos of theta. So if theta is equal to pi by 2, then what will happen? Pi by 2 y of t will be identically 0. Okay, so basically cos theta now becomes an attenuation factor. Therefore the received signal is of course just scaled, but there is no distortion in the received signal, either it amplifies or decreases. The recovered signal or received signal is still proportional to m of t. Okay, when theta is equal to 0, then y of t is equal to k times m of t. When theta is equal to 60 degree, then your y of t is equal to k times m of t times cos of 60 degree. Okay, so again this cos of 60 is constant, and this k also constant. Therefore constant times m of t means it is scaling up or scaling down, that's all, it is not disturbing the message signal. So even if there is some phase distortion, I mean phase mismatch, then no problem, there will be no distortion in the recovered signal. But the problem is when theta becomes 90, completely the signal will be eliminated. Okay, so when the theta equals 90, then completely the signal will be removed. So the problem we do have now is we do not have the recovered signal at all, particularly if your phase difference is as much as pi by 2. So you can see there is a perfect phase matching required. If phase that is phase synchronization is required. Phase synchronization is required. Okay, so this is in one aspect. Now in the case 2, in case let us assume the phase is completely perfectly matched at 0 degree and this delta omega is not equal to 0, then in that case what is your output? Okay, just to simplify the discussion I am taking this type of cases. Okay, so again of course okay, this does not really simplify too much even in this condition also. So y of t is equal to k times m of t and cos of delta omega t. Now you can see there is a distortion as well because you are getting a function of time here. See, this is function of time. With respect to time, your m of t is distorted with respect to time because you are getting a function of time which is not the same function of time, okay, that you start with, that you want. Okay, it is being multiplied by another time function cos omega t. Your m of t is being multiplied by another cos delta omega t time function. So it is the product of two time functions. One is m of t and some additional time function cos of delta omega t, which okay, which is coming in the process again. So that is we don't want. Okay, and one you can ask a question, can we eliminate this through a low pass filter? Through a low pass filter? The answer is no. Why? Because this delta omega is very less, maybe around 1 hertz to 10 hertz, or sometimes people will say 0.1 hertz to 1 hertz. Very less. It's a low frequency, so that low frequency cannot be eliminated by the low pass filter. Okay, so please remember that this is the again modulated signal again because the carrier frequency is extremely small. In the previous case, if you take here, what is the carrier frequency? Carrier frequency is cos omega ct. If you look at here, m of t is multiplied by very high frequency. Let's say omega c is equal, fc is equal to 1000 kilohertz. But this is DSBSC, double sideband suppressed carrier. The same type of situation occurring here also, but here the carrier frequency is how much? Very low frequency, 1 hertz. Okay, it's extremely small. Even if it has a high frequency, the low pass filter would not remove it because the whole thing k times m of t is transmitted around that frequency. So in that case, the low pass filter would not remove anything. Okay, but the important case to discuss here is the case where delta omega is very small. Okay, because that is likely practically happen. Suppose you are designing a local oscillator, even if there is a mismatch, very small mismatch will be there in the carrier frequency. Okay, so we will have a local carrier. We will try to adjust the frequency to be as close to that of the incoming carrier. But maybe there is a very small frequency difference left that we will not be able to take care of that, at least in this case. Okay, so as I said, this delta omega may be of the order of a few hertz. Okay, maybe at the most 100 hertz or tens of hertz. So typically could be tens of hertz, very less. So if you are using very stable oscillators both at the transmitter as well as at the receiver, then the typical frequency will not be that high. Okay, so which will be the case in practice. So in that case, basically what you see is the cos of delta omega t multiplied by the m of t. Okay, and that will be slowly varying sine wave multiplying the delta omega t. See, cos of delta omega t, this is a sinusoidal wave, right? Sinusoidal wave, and the sinusoidal wave is multiplying your m of t. Okay, m of t is very low, m of t is a low pass signal and del omega is typically small. So what will you see in the frequency domain? We will see that your incoming signal is multiplied by a scaling factor, which is sometimes growing up and sometimes reducing significantly. See, based on the time t, your cos of delta omega t is either increasing or decreasing, right? So based on that frequency, there will be some shift. Okay, so some of the amplitude that will go up and then will come down and then go up and come down and so on and so forth. So you will get a distorted version of an actual signal. At one point of time, some signal will go up and some signal will go down, and at another point of time it is giving some other multiplication, because essentially your m of t is multiplied by not constant. If it is constant, no problem at all. If you multiply by a constant, no problem. But if m of t is multiplied by time varying quantity, then you are in a trouble. So that will give the distortion. Therefore, you will get a distorted version of actual signal, and this kind of distortion results what is called warbling distortion. WRB, warbling distortion. Okay, so this is a kind of warbling phenomena. Amplitude going up and down is called a warbling effect. Okay, let's say your this is my m of f. Okay, now because of that cos of delta omega t, then what happens? This slowly moves like this in the positive direction, small amount. Whole m of t will move like that. Okay, so this is slight change. The entire spectrum moves to the right, or because of this warbling phenomena, the entire spectrum moves to the left hand side like this. Okay, this is called this shift is called warbling effect. Okay, so this is your original signal, and this dotted line, these two dotted lines indicates warbling effect. Okay, so if you sum these two spectrums, this spectrum and this spectrum, these two dotted spectrum, then let me draw here. Then instead of in the slightly, your spectrum will be increased like this. So this point is B and this point is minus B, but what about this point? B plus that delta F, and this point is minus B minus delta F. So slightly your bandwidth will be increased. So the sum of these two dotted spectrum you will get at the output. So there is a slight frequency shift to the left as well as to the right. This is the frequency shift to the right, and this one is shifted to the left. So what we will see as the result of these two is no longer a original spectrum. What is the original spectrum? This one is the original spectrum. This one is the original spectrum. Okay, so this is what happening in the frequency domain. Okay, so this is therefore is called a warbling effect. Therefore that underlines the importance of what we call carrier recovery in this kind of modulation. So we recover a fairly sophisticated, a fairly good carrier recovery system by which we will be able to establish the carrier, establish the local carrier, which is perfect in phase and frequency. okay, with the incoming carrier, and that operation is called recovery the carrier at the receiver. So the carrier recovery circuit is needed at the receiver. We have a separate circuit called carrier recovery circuit. Therefore, you can match perfectly between the carrier of the transmitted signal and the carrier of the local oscillator. Okay. So the carrier recovery circuit is needed at the receiver. Now you can ask a question, what will this carrier recovery circuit will do? It produces a coherent local carrier. The purpose of this carrier recovery circuit, it's an electronic circuit, is to produce coherent local carrier. That means it produces a synchronized carrier. And this kind of recovery can be done by using a device called phase locked loop. Phase locked loop. In short, people will call PLL. Okay, which we will discuss a little later. So a special circuit one has to make to carry out this recovery operation, to make sure that the local carrier is in phase and the frequency synchronism with the incoming carrier. And that's why synchronous demodulator is typically a complex operation. Okay, so because you need to worry about this, we need to worry about carrier synchronization. And you may ask a question, because the receiver is a little complex because of this phase locked loop carrier recovery circuit, you can ask a question, why can't we transmit the carrier? Okay, so that is precisely what we are going to discuss next. So if you include the carrier, then that is called a double sideband with carrier. Okay, now whatever we are discussing till now, this all are called without carrier. So if you include the carrier, then it is called, sometimes people call conventional AM conventional amplitude modulation, or double sideband with carrier amplitude modulation. Okay, so that we will see in the next lecture. But if you do that, then there are certain disadvantages. Okay, like there are certain advantages as well as certain disadvantages that we will see one by one. Okay, so like a double sideband with a suppressed carrier modulation, we need to carry out synchronous demodulation, which has this complication like a phase locked loop and all. Okay, so in the next lecture we will explore the possibility of a scheme in which we actually transmit the carrier also. So if you transmit the carrier also, then no need of this phase locked loop and all, because already have the carrier, right? With the help of the carrier you can do the demodulation. So let us see in the next lecture, okay, whether that helps us to simplify the receiver. Okay, so in the next lecture we will talk about double sideband AM with carrier. So let me stop at this point. Thank you very much.